Hello, class. Let's get started with our Earthquake at-Home Kitchen Lab. The lab objectives for this activity are to review plate tectonics and plate motion, practice using triangulation to locate an epicenter, model elastic rebound, model stick-slip fault behavior, use an analog model that you'll build yourself to collect data, that you will collect in groups and use to characterize past earthquake behavior and make future forecasts. So let's get started. You should budget 3 to 4 hours for this activity. You should budget 3 to 4 hours for this lab at home, assuming that you have all of the materials that you need to make your earthquake machine model. So to begin with, I will guide you through a little bit of a review of tectonic motion that you should remember from your reading and from class. And if not, there's a slight review. And then I'll show you how to use Google Earth to do the triangulation portion of your at-home lab. Following that, we'll look at the earthquake machine, which will take you about an hour to put together and then use to collect your data. And I will give you a brief overview of that, but you should budget around an hour, and then you should budget around another hour to do the prediction part of this activity, which isn't really prediction, it is characterization, as you will come to learn and reflect upon at the end of our lab. So to begin with, let's review. What is an earthquake? Take a moment, think about it. This is the release of built-up energy from the movement of tectonic plates. So where do earthquakes occur, and why? Well, I've just told you it's the release of energy from the movement of tectonic plates, so that should take care of the why. So where do earthquakes occur? Well, all over the world. And if you look at this map that I've pulled from a website you will be using in this lab activity, you'll see that there are a few distinct lines. If we follow along the west coast of North America, down the center of the Atlantic Ocean, all around the Pacific Ocean, these are at plate boundaries. So that is one place where earthquakes occur. But they also occur in places that are not on plate boundaries. For example, we have in the Himalayan plateau, we have in the center of North America, we've got in the center of Africa. There are many places where earthquakes can occur. So they're the result of interactions along different plate boundary types, and along each of these types, the depth and magnitude will vary. And this is largely because the thickness of plates changes around our globe, which is an oblate spheroid, and the motion direction is varying, the motion speed is varying, and the motion behavior is varying. And furthermore, as I just pointed out, earthquakes are not only along plate boundaries. Sometimes they're along ancient plate boundaries that are no longer active. Sometimes they are in the center of plates as a result of other processes. So what do we need to know to make educated decisions about future earthquakes? Because as a human species, we are interested in the way that Earth's natural processes negatively impact us. Well, we'll take a look at this intraplate map here from Oklahoma. And you can see this is documenting seismicity from 1973 to 2017. And there are a lot of things being shown on this map besides just locations. But location is obviously an important component. You can see on this map there are earthquakes, these are indicated in the dots of different sizes, that are spread across Oklahoma and Texas into Kansas, etc. You can see that the colors are indicating the time frame within which these earthquakes occurred. So each different color is a different bracket of time. And then you can also see that the size of the circle is indicating something. And in this case, that is the magnitude of the earthquake, how big the earthquake is. So the bigger the circle, the bigger the earthquake that is marked. And then on top of that is the chance of damage for 2017 based on this information. So this is what we need to know. Where, when, and how big. And this is the sort of information that you are going to be modeling and calculating in your lab at home. So to begin with, we need to know what kind of information to gather. So let's first recall earthquake body waves. These are the waves that are of interest to us for this activity of earthquake location. So for earthquake triangulation, we need to look at P waves, which are the faster waves, and they have this push-pull motion. I'm going to demonstrate with a slinky here. So the way that this motion is transmitted through a slinky with compression and extension is the way that P waves move through the Earth's interior. They are faster, so they will leave the earthquake and arrive to the surface of the Earth first. The second waves to arrive are the S waves, or the secondary waves, and they have a shaking-like motion, a side-to-side motion, demonstrated by the slinky here. So these are leaving the earthquake hypocenter at the same time as the P waves, but they arrive to the Earth's surface second. So there is a difference in P to S wave arrival time on the Earth's surface. And that distance in time is what's important for us to figure out when and where the earthquake began. So if we look at a somewhat complicated set of diagrams, what we have here on the left is a set of seismographs, and what we have here on the right is an example of seismic stations being used to triangulate the epicenter or the surface location of the earthquake. The three seismograms, you can see pulses of earthquake energy being shown as these waves on the graphs. And you can see for each of the locations, the size of them and the duration of them vary. Triangulation is so named because there are 3 points that are a minimum required. And if you were to connect stations 1, 2, and 3, you would draw a triangle. Let's look at the same diagram again, but simplified. So here we have 3 much simpler seismograms, excuse me. And marked on here in green, I've labeled the beginning of the P wave and the beginning of the S wave for each of them. These are where the background wiggle of the seismograph changes to indicate the recording of a seismic wave by the machine. So the first big jump in action is what we're looking at. So you can see for each of these locations, the distance on the graph, which is representing time in seconds, is different. So at sensor 1, it's the shortest, and at sensor 3, it's the longest. And that time span is directly related to the distance from the earthquake. Once we have that information, we can use the distance from the earthquake to draw a circle around the location of the station. And you can see here for sensor 1, 2, and 3, each of these circle diameters is different. And the radius of that circle is represented by how long of time there was between the P wave and the S wave arrival. So I'll say that again, hopefully clearer. The time in seconds between when the P wave and the S wave arrived at a location is directly connected to how far away that location is from the earthquake. So each radius of each circle is the distance that is represented by the time it took for the S wave to arrive after the P wave arrived. And this is calculating distance using the SP time difference. Now for your lab, you're not going to be doing that part of the calculation. You'll be given distances directly. Once you have those distances, you're going to be using Google Earth to draw those circles to make your own triangulation solution. So to draw circles in Google Earth, you're going to open Google Earth and you're going to need this measuring tool right here. It looks like a little ruler. So you'll click on that, and when you click on it, it'll open a new window. And that window will give you a whole bunch of options, and one of those options is a circle. When you click on the circle, you get to choose some other information. So the radius, as I've just told you, which is going to be determined by the distance from the epicenter, which is directly related to the duration of time that passed between the S wave and P wave arriving, you can set that to be in kilometers, and that's what you're going to need to complete this lab. You don't really need to worry about the area, just make sure the units for the radius are in kilometers. Then once you've done that, you can go ahead and start drawing your circle, which you'll do just by clicking and dragging on the map. And as you do that, so here I started my location and I clicked and dragged to make my circle on Google Earth. And as you draw it, you can see in the ruler tool just how big that radius is. So if I was aiming for 2,000 kilometers, I just have a little bit longer to go before I get there. And then once I have my radius at the right length, then I can hit save and I have a circle representing the station information that I need for my lab. So in your groups, you have been assigned locations. These locations are representing seismic stations, and you've been given them in latitude and longitude. So you'll need to plot all of these into Google Earth. Each of these seismic stations, you've also been given a distance in kilometers, that is the distance to the epicenter of the earthquake. So now you know you'll need to draw circles for each of these locations. You have more than 3. This is because this will increase your accuracy, and that is something that you'll reflect on later on in the lab. So after you draw your circles, you'll triangulate the location of the epicenter using Google Earth and then estimate this location, recording the coordinates in latitude and longitude for your lab. Check your triangulation results against your group mates. So let's have a moment there for you to think about and reflect with your group mates how accurate your location estimate is and what the sources of error might be. Once you've done that, you're going to move on to part 2 of the lab. For part 2, you're going to build an earthquake machine. This is an analog model representing the motion that occurs during an earthquake or building up to and then after an earthquake as a result of tectonic plates. So in this particular photo, I'm showing you a first run earthquake machine that I made. This earthquake machine I built using a piece of wood, a gift bag that I glued a piece of sandpaper to the bottom of, some rubber bands, a string, and then there's a small weight. It's a few bolts inside of this paper bag. And this is just set up on the kitchen table. I'll show you another example in just a moment. For this earthquake machine, we have to have a resistant surface, which can be a board of wood, it can be the carpeted floor at your house, it can be any number of things. And then you need to have your weighted, also friction surface representing the tectonic plate that is moving. In addition to that, we also have the elastic, which is a really important component. String is simply for pulling. It makes it easier than you holding onto the elastic so that you can record the measurements more easily by yourself. So for each of these parts, the elastic representing the elastic properties of lower crustal rocks is super key in this particular earthquake model. It will behave differently than the sandpaper-backed weighted bag, which is representing the locked part of the fault, the part that, when it releases, results in an earthquake. I've given you a rate of motion for the string, which is what you should try and pull the string slow enough that it's representing 1 centimeter per year. So in your groups, you'll each have earthquake machines that you have built. So in your kitchen lab at home, each of you will have used different materials, which means you'll have different elasticity and you'll have different stick-slip fault behavior. And that's great because that'll help you collect a variety of data. So you're going to use your machines to model and then explain, after you've collected your data, these behaviors. To collect the data, you'll need to measure the starting and ending distances for several earthquakes in your models. And that might mean that depending on your particular earthquake machine, you'll have to do several runs yourself. But the idea is for you to collect data amongst your group mates, and then all of you will contribute to the data set. So the things you need to collect in this part of the lab activity are the pulling distance. This is pulling the string. So that is how far you've pulled for the end of the elastic, and this is going to represent time. The other thing you're going to collect is slip distance, which is going to represent the magnitude of the earthquake. And this is simply how far your locked end of the plate moves. So to illustrate that with the board, on the board, that means we're looking at the start for the movement distance and the start for the pulling distance. So the start for the pulling distance is going to be the end of your elastic, and the start for the slip distance is going to be the back end of the plate, the locked plate. Once you pull it, so you can see now the earthquake has happened, the weighted bag has moved forward, we're looking for the stopping distance. From where it began to where it ended is how far it slipped, and from where the elastic began to where the elastic is now stretched is the pulling distance. So the distance that the plate moved, you'll record as centimeters, representing the distance of plate movement, and the other part you'll record as time. Remember, you're representing this pulling as 1 centimeter per year. So if this moved 20 centimeters, that would represent 20 years. This is an example of how you might build your earthquake machine. We've got a few simple components, all of which you can pretty easily find or make at home. I've got a gift bag here, and I've glued a strip of sandpaper to the bottom of it. And inside you can see is a can of black beans to provide some weight. And this is going to represent the tectonic plate in our earthquake machine. Here we have an elastic band. This elastic band is going to represent the elastic component of the tectonic plate, which accommodates the strain buildup in the rock before movement from an earthquake releases that energy. We've got 2 tape measures. You can use rulers, you can just measure out some string and mark it, whatever you have at home. This one is lined up with the beginning, the 0 marker at the back end of the bag with the plate. And this one is lined up with the top end of the elastic band. From here, there's 2 measurements that you're going to make in your lab. One is going to be along this tape, and the other is going to be along this tape. So when you set up your lab notebook, you'll need 2 columns. One to measure the amount of movement of the plate, which is going to be read off of this tape, and the other will be measuring the amount of stretch in the elastic band, which will be read off of this tape. To operate the earthquake machine, you're simply going to stretch the elastic band, measure how much strain there is before it moves. So I'm keeping my eye on the elastic band. I can see now it's at 15 centimeters, 16, 17, 18, 19, 26, and you can see the plate moved. So I would measure on the other tape how far that plate moved in that single earthquake. It's important here that I'm holding the elastic tight and I'm not letting it recoil back, and I'm going to have the 0 point for where I start measuring how much strain is built up in the elastic band be where it's ended here. So right now it's at 26 centimeters, and as I continue pulling, it's going to be pulling from that 26 centimeter mark onward. Earthquake number 2, and so on. So now you're going to use your group's data to put together a graph representing the number of earthquakes and the amount of slip. And you're furthermore going to put bins along this graph x-axis that will represent each of them a range of amounts of slip. So for example, you might say 1 to 2 centimeters for the first bin, 2 to 4 centimeters, 4 to 6, or you might do 1 to 5 centimeters, 5 to 10, etc., depending on how much data you have and how big your biggest earthquake and how small your smallest earthquake was. The earthquake count is simply the number of earthquakes. So within your group, you'll want to have enough data to plot on this graph that you can actually start to see a trend from your earthquake machines. So this is important because we use data just like this from the real world and from real earthquakes to determine something called the earthquake mean recurrence interval, or MRI. This is what's used for scientists to calculate the probability of large earthquakes occurring in the future, especially if they haven't happened in the recent past. Whenever you hear talk about the big one on the west coast of BC, Washington, Oregon, California, this is something we are expecting, but we haven't recorded with modern machinery in the recent times. So this is just an article from Montana as another example where the scientists say a big earthquake is a possibility, but there's no way to predict when that could happen. So I want you to keep that in mind as we proceed through the rest of the lab. So this graph should look familiar. This is something very much like what you are making. You see we have earthquakes per year. This is your earthquake count. And on the x-axis, you have the magnitude, or the size of the earthquake. Now, in this case, we've got a range here from magnitude 3 to magnitude 4. You should review in your textbook what those magnitudes are, and then you can think about how the bin categories for your own data are being represented in your graph, comparable to this one, for Utah in the Wasatch Intermountain Seismic Zone. So this is what your graph might look like with the amount of slip and the earthquake count. This is from my own data that I collected from the first run of this exercise testing at home. And you'll use this to plot trends. So from your own data to the next part of the lab where I've given you data to look up using the IRIS earthquake browser, which is a searchable database of global earthquakes from as long as we have them recorded. So you will use 30 years of earthquake history outlined in the lab instructions. So use 1990 to 2020 that you can input in the IRIS website, and you'll use that to determine the probabilities of magnitude 6 to 6.9 and 7 to 7.9 earthquakes over the next year and over the next 30 years, following the instructions I've provided for you and comparing how these probabilities look relative to the graph that you made from your at-home earthquake model. To use the earthquake browser, you'll go to the website I've provided, you'll choose a location. Here I've arbitrarily chosen Montana. This is where that map that I showed you, or the newspaper article I showed you earlier, came from. And from this box that you can draw by clicking on Select New Region and simply clicking and dragging to draw a box around the area of interest. You can then use the toolbar on the right-hand side to input the time range. That would be 1990 to 2020. The magnitude range, you'll look up each magnitude at a time for each of the bins of the graph that you'll be completing. You don't need to set the depth range, and you don't need to set the data source either. But by looking up the specific time range and the magnitude range, you can simply input the most recent data from this database into your graph and use that to determine the answers for your lab. So this is the table you'll be filling in with the data that you get from the IRIS earthquake database. You'll input the data that I just was telling you how to outline in this first column B. Then you'll follow the instructions in the tutorial I've provided for you to complete columns C and D and calculate the mean recurrence interval. Then once you have that, you'll use that information to determine the 1-year probability and the 30-year probability of earthquakes in your assigned area. To do that, you're going to need to plot on a graph that looks very much like the graph that you've just made for your analog model. The bins are already set for you on the x-axis by earthquake magnitude. Now on the y-axis, instead of an earthquake count, you're actually putting in the mean recurrence interval in years. And this is a log y-axis graph. So each of the lines you'll see have different distances on them, and we'll just look at 10 to 100 for an example. As we move from this 10 marker up, this next line is 20. The next line is 30, then 40, then 50, 60, 70, 80, 90, until you reach 100. For the next one above that, the first line is 200. So we go from 100 to 200, 300, 400, 500, etc. And similarly, from 1 to 10, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's a little bit different to plot on a log y-axis graph, but you will get the hang of it, no problem at all. Once you have those plotted, you will indicate a trend through them by drawing a line of best fit. You can draw that in PowerPoint, on a tablet if you have a tablet that you're using. If you have a printer, you can print and draw by hand. Any of those will work. So your line of best fit might look like that. It really is your best guess. You want to hit as many of the points as possible. And from there, you can read off on the graph where the data values that you don't have would lie and extrapolate those to fill in the blanks in column D. You'll see this in the instructions. So there you go. Now your last part of the assignment is to reflect. So you have some questions in the lab, but the big part of this assignment is for you to think about this idea of earthquake probability and prediction. You have to think about how much we know or don't know. I want you to think about how big the earthquakes are and what the potential impacts are. What is the difference between a magnitude 6 and a magnitude 7? You have this information in your textbook, and I want you to apply it to the location that you have been assigned. Then finally, as I alluded to, you're going to discuss the conundrum of earthquake forecasting, given this experience that you have with calculating statistical probabilities, plotting earthquake locations, and measuring using your analog model that you built yourself.